So this is a continuation of the problem we did in the previous video. What if instead we were to use 10 molar HCl in this process? I'm going to jump right into the Nernst equation. I'm going to say that E of our cell will be equal to E0 of our cell minus 0.0592 divided by N, which is 2. And then what we will have is the log of all the different concentrations. We will have Mn2 plus, we will have PCl2, we will have H plus to the fourth, and Cl minus squared. So how are you going to know the individual concentrations of the ions? Well, HCl is a strong electrolyte and a strong acid. It totally dissociates into H plus and Cl minus. So if I look at this expression, what I will have here is, let's do some substitutions. E of the cell will be equal to minus 0.13 minus 0.0592 over 2. It was a 2-electron process. Then we will have the log of 1.00 molar, 1.00 ATMs, divided by 10 to the fourth and 10 squared. Now, when I put these values in, remember this is reference to 1 molar, this is reference to 1 atmosphere. So you actually can mix molarity and pressure measurements. If I look at the bottom line for this, E of the cell is going to be minus 0.13 plus a 0.18, which will give me a positive 0.05 volts. Note it is a positive sign. So changing the concentration has changed the direction of the reaction. Be aware that's a possibility on midterm 3, where we really want to see, can you understand how to use the Nernst equation? I had a second slide. I don't think I'm going to need it for this problem. But let's move on to this next example on how a voltaic cell can measure pH. This is a plain expression. We've seen this before. Here is the H plus, and essentially you can measure the pH of a system as you use the Nernst equation. So how do I want to do this one? Well, I'm going to start again. E of a cell is equal to E0 of the cell minus 0.0592 over N, and I'm going to say log of Q. So what do we want to do in this problem? Well, I'm going to have you solve for Q rather than do something else. So let's put in what we know. 0.45 volts, 0.76 volts, that is calculated. I stole that from sample exercise 20.12. That's really what this is. Then we have a 0.0592 over 10, and we're going to leave it right now as the log of Q. I want to work through the math. There's a minus 0.31. It's equal to a negative 0.0296 times the log of Q. Then I will get a 10.47 is equal to the log of Q, and Q is going to be equal to 10 to the 10.47. That comes up to be 2.95 times 10 to the 10th. Now, what is Q? Well, you know, we kind of ran out of space on this slide. So let's look at another one. If I look at my expression from the equation, my Q is going to be Zn2 plus times the pressure of H2 divided by H plus squared. I know that the zinc is given to me as 1 molar. The pressure of H2 is 1 atmosphere. So Q turns out to be 1 over H plus squared. Let's put in the value we got for Q. Q is 2.95 times 10 to the 10th, and it is equal to 1 over H plus squared. H plus squared is now equal to 3.38 times 10 to the minus 11, and H plus is equal to 5.82 times 10 to the minus 6 molar. pH is minus the log of H plus, and that gives us a pH of 5.23. So again, a Nernst equation can be used in order to find a pH. Another example, very, very low concentrations can actually be measured by electrochem. Now this problem states the shorthand, and you may see this on your exam if you've done the practices, you've seen the shorthand. You know that this is the anode where we have oxidation. This is the cathode where we have reduction. So I'm going to leave it up to you to write the equations, but what I'm going to calculate is the E0 of the cell. It's going to be the E0 of what's being reduced, Ag plus to Ag, minus the E0 reduction of what's being oxidized, which is the CD to the CD2 plus. I looked them up in the back because, you know, we're doing a problem like a homework problem. 0.80 minus a negative 0.40, that gives me an E0 cell equal to 1.20 volts. Now again, this comes from the beginning of the chapter. There's no reason to run away from these problems because they're not really hard. Let's move to a fresh slide to work the Nernst equation. We're going to have E cell is equal to E0 of the cell minus 0.0592 divided by 2 times the log of my balanced chemical equation. I have CD2 plus as the product. I have Ag plus squared as the reactant. You could consider this Q, if you'd like to make this problem work a lot prettier, okay? So let's put the numbers in. I have a 1.44 equal to a 1.20 minus the 0.0592 over 2, and let's just call this the log of Q. As we do our math, we will see that minus 8.10 is going to be equal to the log of Q. I combine the math. And Q is going to be equal to 10 to the minus 8.10. That turns out to be 7.9 times 10 to the minus 9 molar. Now, what does that represent? Well, Q is equal to CD2 plus over Ag plus squared. They have told us that the concentration of Ag plus is 1 molar, so that means that Q is going to be equal to the concentration of cadmium 2 plus. And that is the value that we got by concentration. So again, we really can learn about low concentrations by using the Nernst equation. My last example is concentration cells. And as we've worked through these last examples, you're saying, oh my, why do I have to know this? Well, concentration cells are really EKGs. What they do is they measure the potassium ion going in and out of your heart muscle. That's a specific. But a concentration cell, what it does is it uses the same half reaction for both half cells. The cells must have different concentrations, and we will always make the more dilute solution be the anode. So I'm going to do the heart afterwards, but here I'm just going to do a plain old copper. And since this is important because it does have a real-life application, let's write out the two different reactions. Let's write out the cathode reaction. Cathode is reduction. Cu2 plus aqueous plus 2 electrons goes to form copper as a solid. And again, that is the cathode reaction. If I look at my anode reaction, I have Cu as a solid going to form Cu2 plus aqueous plus 2 electrons. Again, this is to help you see where does this come from. And if you look at the E0 of reduction, you can look it up. It's 0.34, 0.34. So my E0 of my cell turns out to be 0, one minus the other. So let's move on just a tiny bit more, okay? Let's do the E cell for this copper problem. The problem will say I have 0, 0, that is my E0 of my cell, minus 0.0592 divided by 2, and I'm going to write these concentrations in. I'm going to go 0.010 divided by 1.00. What we have on the top is the reaction from the anode, the concentration. What we have on the bottom is the concentration from the cathode. And as we work through this problem, you'll see why we set it up this way. It is so that we come with an answer of 0.0592 volts. So a concentration cell has a positive EMF so that it is spontaneous in the forward direction. And again, we're tying all of the chapters together now. We could go in E, we could go in G. But what I want to wrap this up with is your heart, okay? So in looking at a medical application, we would still have the Nernst equation. E is equal to E0, but since our bodies are not at 25 degrees centigrade, what we would have to do is go back to the massive constant evaluation. And we would use in this place the log of the potassium on the intracellular fluid divided by the potassium for the extracellular fluid. And if I look at those numbers, I'll place them in the next line. I'll say E is equal to 0. That's our E0 cell. It's potassium in and out. And it'll be 61.5 millivolts times the log of just some chosen concentrations that really are part of the system. And what we would have is 135 millimolar divided by 4 millimolar. Now, the whole reason for doing this is so you can see that the E for this is a minus 94 millivolts. Notice, it is not a spontaneous reaction. So, your body needs to do work to keep your heart pumping. And if someone's body can't do the work, what they will implant is a pacemaker. Often I've had students who do have pacemakers, and they're kind of excited when they see this because they know a lot about their pacemaker, but they probably never saw the Nernst equation.